Okay, today we're going to talk about hash tables. And a hash table allows rapid insertion, retrieval, and removal of elements in a collection. So if we compare this to the data types we've looked at so far, the safe array and the linked list, let's talk about the safe array for a second. The safe array we know is this array-based container where we store things, but then we also have this kind of additional space that is allocated but not used. So insertion and removal is generally fast. So if this is the last item that was inserted, well, to insert another item we just increase that index by 1 and we put a value there. Right? And now that becomes our last one inserted. When we insert another thing, again, we just move that index forward. Okay, it's true that insertion and removal is generally fast, except when we have to double the size of the array, in which case it's really, really slow. So if we had 1,000,000 items in here, and we wanted to add the 1,000,000 and first, what we'd have to do is make an array that's twice as large. We'd have to copy all the values over for the first 1,000,000. Okay. And that takes a really long time. Retrieving is fast if you know the index of the value you want to access, but it's slow if you have to search through all the elements to see if it's there. So in other words, if you know the index is at, or the piece of data is at position 7, it's really easy just to go grab the piece of data at position 7. But if you don't know the position and you have to kind of search, well, the only way you can really do this is start at the beginning and then start looking. Is that the piece of data I'm looking for? Is that the piece of data? Until you get to the end. Okay, and safe arrays really are memory inefficient because we almost always are allocating more room than we're actually using. Okay, so remember, when we go and make that array that's 2,000,000 elements long, now, about 1,000,000 of those slots are not being used. So that's pretty memory inefficient. But it's very processor efficient because of the way RAM works. Right? The processor is not involved with accessing the elements like it is with a linked list. Okay, then we had our linked list based containers. Just a plain old linked list or an ordered linked list. The idea is the same. We have nodes, and the nodes have links to the neighbors. Now, insertion and removal is generally fast here if and only if you're working with either the first or the last element using the head or tail pointers. If you're inserting in the middle, then it's actually fairly slow because you have to work your way through each of the nodes to get an insert position. So starting from the head, if you want to insert in the middle, you have to kind of move to the right position, and then you can do the insert. We saw this is basically big O of n behavior with the ordered linked list, where we had to go and find what's the right position. Now retrieve is slow because you don't have the array notation like you do with an array-based container. You have to move through the nodes to get where you want to go. Linked lists, though, are very memory efficient because we're only allocating room for the nodes we need. There is a little bit of overhead for the pointers that point to the neighbor nodes, but it's in the grand scheme of things, it's not that memory inefficient. But it is very processor inefficient because we have to involve the processor in accessing all of the elements. Okay, so if retrieving items is fast, if that's an important thing for your program and you can afford to be memory inefficient, then a safe array is better. But if conserving memory is important and you don't need to insert or remove in the middle, well, then a linked list is better. And we've also looked at stacks and queues. Those are not really general purpose containers, so I won't compare them to the safe array or the linked list. Okay, the point is, retrieving an item where we don't know the index for either a linked list or a safe array is pretty slow. It's basically a big O of n operation. Okay, and that's where hash tables come in. Hash tables allow us to insert and retrieve elements from it at approximately constant time, or big O of 1 time, regardless of the size of the collection. So let's think about that for a second. With an unordered safe array or linked list, if you wanted to find an element in the container and you didn't know its position, you'd have to manually search from the beginning to the end. Okay? And that's why I say that's a big O of n operation. The amount of work depends on the number of elements that are being stored. With a hash table, what I'm saying is we can retrieve an item in about constant time. I'll talk about why it's about and not exactly later. Okay, so that's the big advantage of a hash table, is you can retrieve items very quickly. It's not based on the number of elements that are in them. Hash tables store and retrieve things based on key value pairs, where a key uniquely identifies a value. And usually a key is an integer number of some kind. Okay, so some potential key values might be like a social security number. Okay, that identifies, a person. And maybe a part number. Well, that identifies a part. And I don't know, maybe a flight number. Well, that identifies a flight. Okay. So that's what the value part of this is. The key identifies the value. Okay. These values, or the keys, I should say, must be unique for each value. Every person has an individual social security number. No two people are supposed to have the same one. The value in the key value pair can be anything. So the key should be an integer, but the value can be any type of object. So let's imagine for a second we were keeping track of information about students. Right. Well, the key will be what I'm going to call the social security number, or I guess this is really more of an ID, because it's shorter than a social security number, but the value would be an entire student object. Right. And we know, of course, we can create things like this. So this might be a student object where the first part is the ID, and we have a first name, and a last name, and maybe a GPA. Okay, we can certainly create a class or a struct to represent a student, and this whole row represents basically a student. Okay, we could then use the social security number as a key and the student object as a value in a student array. Okay. Then all we need to do is create an array of student objects and use each student's social security number as an index into the array. Now imagine we had an array of students. Right, this student's ID is 238, so we'd go to the array at position 238, and we'd store this guy's information here. So this was Joe. He had a 3.5 GPA. Okay. So the idea is you use the ID as an integer, which is an integer, as an index into some array. Okay. Now let's kind of recall how our memory works, our computer's RAM. So I think I've talked about this before. We think of RAM as this long series of boxes. Okay, and there's actually these wires or lines that come in and go out of the RAM. Okay. So these are called the address lines. Okay, and data kind of flows in this way. So we put some address, some numeric address, on the lines that go into the RAM, and then you wait a short amount of time, and the value at any one of these boxes, so if this was the numeric address of this piece of data, well then the data inside here would be fed out on these things called the data lines. Okay. So you feed in a number, which is an address, you wait a very short amount of time, and then the data in that box will be sent out the address lines. Okay, and this is what makes RAM super fast, is accessing the first element takes the same amount of time as accessing the 1/1,000,000th element. There are no moving parts here. It takes the same amount of time to grab the first thing as it does the last. So we apply these electrical signals to the address lines, feeding into every cell. We wait a short amount of time, and then the data comes out the data lines. Okay, so this is great. Now if we do that, if we use a student's ID as an index into the array, you should be able to see that we can get insert and retrieve to be very quick, basically a big O of 1 operation, a constant time operation. We have a problem though. The range of Social Security numbers is from about 0 to 1 billion. So if we want super fast access time, then we're going to have to allocate an array of 1 billion student objects. So let's kind of see what that would look like. Okay, so the index of the first one would be 0, and the index of the very last one would be somewhere just short of 1 billion. And in this case, we only had really a few student objects. And we had that student 238. Okay. Now, a school with about 2,000 students, this wastes about 99.9999998% of the memory, meaning it's virtually empty. This array of 1 billion items is virtually empty. And this again is the classic trade-off when we talk about programming. It's the time versus space trade-off. If you want it fast, you can have it fast, but it's going to cost you in memory space. So here we can now retrieve any student very, very quickly, okay, but we're wasting a tremendous amount of memory. Similarly, if you want to limit memory space, that usually costs you in processing time. Okay, so this is a problem. We can't have these incredibly sparse arrays. It's just tremendously inefficient, memory inefficient. So what we do to avoid this is something called hashing. And hashing is the process of mapping one set of values to a smaller set of values. So we have this big range of values for Social Security numbers, somewhere in the range of 0 to about 1 billion. And we want to hash to a much smaller set, maybe between 0 and 10,000. Okay. If we can do this, then we can make an array that's much smaller and much more densely packed. So if we could take any Social Security number and hash it into a number that's smaller, between, say, 0 and 10,000, then we can create a much smaller array. And fill a lot more of this data with actual students. Okay, so that's the idea of a hash table. Is we take the key value and we hash it. We take it from a large possible value to a much smaller one, and then we store the objects in this much smaller array. So we will have eliminated most of our space inefficiency while maintaining our pretty good processing speed. Now, a collision occurs when two values map to the same hashed value. So when we're mapping from a number in the range of 0 to 1 billion to a number in the range of 0 to 10,000, it's bound to happen. There are going to be collisions. Right? This is not a one-to-one mapping. A hash function should be a simple arithmetic operation that doesn't take a long time to perform. The hash function should spread the hashed values out evenly, or as close to evenly as we can come. Straight division is usually not a good hashing function if the key values tend to cluster together. So we're talking about Social Security numbers earlier. Everyone's Social Security number is at least partially determined by where you were born. So mine starts with a 3, and I would guess most of yours do too if you were born in this part of the country. Okay, so let's look at straight division, which is definitely a nice simple arithmetic operation. But let's say we had some key values, like this. Okay, so these are definitely unique key values. If we decided our hash function was going to be a divide by 100, so basically we will take our key and divide that by 100. Okay, what we see is we get the same value. We get a collision for these keys that are really close to each other. They have clustered, the keys are clustered together. And if we do a straight division by 100, we get these collisions, meaning unique keys hashed to the exact same value. Now it turns out using modulus division with a prime number does a really good job of spreading the values out. Okay, so let's take the exact same values. Keys. Right, and instead of doing a straight division, we'll do a modulus division. And instead of using 100, we're going to use a prime number. So 101 is a prime number. And if we take 12,345 and we mod it by 101, you can do the math by hand if you want, but the remainder is going to be the value 23. And for this one, the value will be 24 and 25. So even though these keys tended to cluster, they're close to each other. If we mod divide by a prime number, it kind of spreads the hashed values out. And that's what a good hash function will do. Okay, so let's imagine we wanted to store 10 student objects in a hash table. So 10 is not a prime number, so we're going to find the next largest prime is 11, and we're going to make an array that is exactly 11 elements long. So an array with 11 elements will have index values from 0 to 10, and our hash function is going to be this. We're going to take the key and we're going to mod it by 11. Okay. Now the result of modding by 11 is always going to be in the range of 0 to 10. Okay, and notice that's exactly the same range of values for an 11 element array. Okay, so let's say we were going to start storing some students inside this array of student objects. So every student has a student ID, and then we'll also look at the hashed value. And what I mean by a hashed value is feeding the student ID through the hash function and getting the result. So let's start with student 238. 238 mod 11 is the value 7. Okay, so what that means is we'll go to this array at position 7 and we'll store that student information there. Okay, so remember he has a name and he has a GPA and he has all that other stuff, but it's the ID of the student that determined the slot in the array where he was going to go. Say we had another student who had an ID of 490. If we say 490 mod 11, if you do the math, okay, the remainder value is 6. Okay, and that's where we'd put that student object at position 6. Student 154, 154 mod 11, that'll give you a remainder of 0. That means the student will go at position 0. Say 233. 233 mod 11 is the value 2. Okay, so we go to position 2, store a student there, and student with an ID of 586. 586 mod 11 is the value 3. So we'd go to the array at position 3 and store the student there. Okay, so the interface to the hash table there'll be an insert function. Right, so we might have insert, and this takes a key and a value. Okay, then we will have a retrieve. This will pass in a key, and the function will return a value. It will return an object from the array. And we might also have a remove, which also will take a key, and just go to the hash table and remove whatever element that has that key. So if we had an actual hash table object maybe called table, and we had a real student object maybe called S1, the way the insert would work is we'd say, well, S1 dot get student ID. Right? That will get the key, and the value that we're going to store is the actual student object itself. So table.insert S1.get student ID, that's the key, and the value is the student object itself. Okay, when we want to retrieve an item, let's go back here for a second. Let's say we were looking for the student with the ID 490. Okay, well, what we would do is we would take that student ID and hash it by this hash function, and we'd say that that object is at position 6 in the array. Okay, so retrieve is kind of just the opposite of insert, or very similar to insert actually, where we take the key and we hash it, and that gives us the location of where to find that object in the hash table. So we do a little bit of math to hash down to a smaller value, but then it's just array notation. We have an index, and we can get very fast access to that position in the underlying array. Now I picked these numbers very carefully. Notice there was not any collision. Let's say we had another student, though, with a unique ID of 623. If we do the math, 623 mod 11 gives us a value of 7. And we have a slight problem here, because we can't just go to the array at position 7 and store the student information there. We'll lose all the information about student 238. Okay, so slot 7 is in use. We're going to have to do something about this. And one way to solve this problem is to use this approach called linear probing. Linear probing says to start looking at the hashed value, in this case 7, and if that slot happens to be used, probe forward until we get to an empty slot. Okay, so when we're trying to insert this value, the student 623, we're going to start at position 7, but that's used. So we're going to look forward to the very next position. And this one's free. This one's not being used. So we can store the student there. Okay, now when we linearly probe, when we look forward like this, we think of the array as being circular. So if we did get to the end and we wanted to probe forward, we would just go back to position 0. I think we did something like that in our queue data structure. Okay, now when retrieving, using this linear probing technique, we use the hashed value as a starting point and look for the object with an ID of the key value until it's found or an empty slot is found. So again, now if we're trying to retrieve student 623, we hash that and get a starting point of 7, and then we just say, well, are you student 623? And here we say, no, 238 is not 623. So we probe forward and we say, well, are you 623? And we say, yes, that's the student we're looking for. Now if we try and retrieve a student and we get a starting value and we probe forward, if we ever find an empty slot, like if we were looking for some student starting at 7 and we probed forward and we found an empty slot, what that means is that student is not being stored in the hash table. Because if it was, it would have been somewhere in between 7 and the first empty slot. And since we encountered an empty slot, we know that that student is not on the hash table. Okay, so if there was an empty slot, that's where that value would have been, so we know the item's not present. Now with linear probing, one needs to know if a slot is filled or not. And this makes deleting elements from a hash table difficult because when you search for an item, you hash on the key to get a starting point, and then you look for it until it's either found or there's an empty slot. But a deleted element is not really the same as an empty slot. Right? Because you could have added one item, right, that maybe landed at position 7, but then if we delete this one, okay, and we look for student 623, we're still going to go and start at position 7. The fact that it's deleted doesn't really mean the same thing as being empty. So we would continue to probe until we got to a genuinely empty slot. Okay, so because we need to know the state of each one of the slots in the array, one thing we can do is we can have a mirrored array where you basically keep the state of the elements either used, free, or deleted. And then we can truly look for whether something has been deleted or it just happens to be empty. Right. So we have our array to hold the data, okay, but then we have this mirrored array that's the exact same size, and we might say, well, this one's free and this one's used and this one's free. This one used to be used, but then it got deleted. It might be free and used. And now when you hash on a value, okay, you start at that position and then you probe forward as long as we have a used or deleted slot. As soon as we get to a genuinely free slot, we know the item's not in there. Okay, so linear probing is somewhat difficult to manage. There's another approach called chained hashing. And we can the idea here is we use an array of linked lists to avoid dealing with collisions altogether. There still are collisions, but instead of having to worry about probing forward, we just add the items to a linked list. Okay, so I said it's an array of linked lists. So this is a very important picture here. Okay, this array has index values. Okay, and what we're going to do is we're going to apply the hash function. Okay, so we're going to hash on a key, and that's going to give us an index into this array. Okay, now each element of this array is a hash table. is a linked list. And what we can do is once we hash on the key, that'll give us a linked list, and then we can insert at that particular linked list. So now when we have a collision, instead of probing forward in the one array like we did before, so let's say we have the student ID that hashes to the value 5, well, now we can just tack on another node to this linked list, when we insert, that's a very fast operation. And when we want to retrieve the student whose ID hashed to 5, we wouldn't know right away because there are a couple students who hashed to 5. But if these lists are short enough, we can just iterate through and say, are you the student I'm looking for? Are you the student I'm looking for? Are you the student I'm looking for? So if you remember nothing else about hash tables, remember this picture here. A hash table, you think of it as just this array of linked lists, where to insert, you hash on the key and tack on that node to that particular linked list. And when you want to retrieve an element, again, you hash on the key to get a linked list, and you just do some probing. You just march through the array list. And the key to making all this work is having really short array lists. And the way we get really short array lists is to avoid collisions, and the way we avoid collisions is having a good hash function. Okay, so if we had many collisions, if we had this problem of clustering, our performance would actually approach big O of n performance. So imagine our hash function was bad, and no matter what the student ID, we always hash to the same value. So here we have a hash table with 6 elements in it. So these values are spread out pretty well. But if we had a bad hash function, right, all 6 students would hash to the exact same position. Let's call this position x. And now retrieving a value, although inserting is pretty quick, we just hash, find a list, and put it at either the beginning or the end. Now to retrieve a value, we have to do a lot more probing, which we know for a linked list is not super efficient. Right? We just have to kind of start at the beginning and march through. Okay, so that's what happens when you have a bad hash function. And again, we get the behavior kind of degrades to a big O of n. Spreading the hash keys out limits the amount of work that it takes to find an element. This is why we say a hash table is about a constant operation. It's about big O of 1 if we use a good hash function. Because again, if we have a bunch of very short linked lists, it doesn't take a whole lot of time to iterate through all the elements of a short linked list. Now, hash tables should only be about 50 to 90% full to capacity. This, along with a good hash function, modding by a prime number, guarantees that the values will be spread out and you'll get that about big O of 1 performance. So for example, if you anticipate that you'll be storing about 100 elements in a hash table, you'd want to double the size to about 200 and then look for a prime number in that range, maybe 199. That's the next closest prime to 200. And then that would be the size of your underlying array. Even though you know you're only going to store about 100 elements, you want to make it about twice as big, and that along with a good hash function, modding by the prime number, will virtually guarantee that you're going to have a bunch of short little linked lists, and that's going to give us really good performance. Okay. Now that's the hash table.